Good morning. This is the fourth video lecture. So in the last class we have we have discussed the system, change of a system, path, process, cycle. So once again reminding that particular content. So a system is going to change when the mass and energy interactions with the surroundings is going to happen. So when the mass and energy interactions within the system with respect to the surroundings are there, then the thermodynamic system or a change in state is going to occur. So the mode in which the change of a state of a system takes place is termed as a process, whether it is a adiabatic process, polytropic process, or isentropic process, isothermal process, whatever it may be, right? So the mode in which the change of a state of a system takes place is called a process. The path refers to the series of state changes. Path refers to the series of state changes. So that means where you can observe the path. This is the path. Series of system change. This is the path, right? So this is one path. Path refers to the series of state changes through which the system passes, right? So that is nothing but the path. Next one is the cycle. So the sequence of process involved in a system, that we can call it as a cycle. So suppose if a cycle consisting of constant pressure process, constant volume, isothermal process. So once if a system property changes from initial state and it will come back to the final state, then one cycle is completed. So that is nothing but the cycle. And one more content we have discussed, it is intensive, that is intrinsic or qualitative property, extensive, you can call it as extrinsic or quantitative property. So the some of the examples are also we have discussed. So the specialty, that means the ratio of the extensive property to the mass is called as a intensive property. Say suppose if you take the specific volume, it is an intensive property. Molar volume, it is an intensive property. So this is what you have to identify from the thermodynamic property. So property once again uh, reminding that some observable characteristic of a system. When you assign a value to the observable characteristic of a system, that we can call it as a property. So that property either it may be the intensive property or it may be the extensive property. If it is independent of mass of the system, you can call it as intrinsic property. If it depends on to the mass and size of the system, then you can call it as a extensive property. So that is the thermodynamics. And the another content what we have discussed is the quasi-static process. So the quasi-static process is nothing but a process which occurs in an infinitely slowly. That you can call it as a quasi-static process. Non-quasi-static process, a process which occurs in a rapid way, that is the very fast process, right? So within a short time, the process is going to complete, right? So that is nothing but the non-quasi-static process. So in a non-quasi-static process, you can also call it as the irreversible process. So you can also call this one as a irreversible process. This is the irreversible process, and you can represent the process as in terms of the dotted line. Whereas in case of a quasi-static process, the process can be represented as a continuous line, that is a firm line. So this you can also call it as a reversible process. This you can also call it as a reversible process. So for today's class, we will discuss what are the examples, connected to the reversible process and irreversible process. So the quasi-static process example is expansion of gases behind the piston against infinitely small weights. So very small incremental weights. Whereas the expansion of gases behind the piston against a single weight, then you can consider it as a non-quasi-static process. So these are the diagrammatic sketches where you can observe. So here the large weight, so it is the 10 kg weight here. whereas this 10 kg weight is split up into kg, small incremental weight. So that is when a system changes from state 1 to the state 2 in a compression process, the intermediate state points are in totally thermodynamic equilibrium. Thermodynamic means it should be balanced chemically, mechanically, thermally. So that you should have to understand. That means the property should be in balance. The property should be the property should have the thermodynamic value, that is it should be balanced condition with respect to the system and the surroundings, whereas in this case the non-equilibrium, that is the quasi-static or the non-quasi-static process. So the intermediate states are in the non-equilibrium states. So this is not going to satisfy the thermodynamic equilibrium. This is not going to satisfy the thermodynamic equilibrium, right? So this is the content of what we have discussed in the class. So connected to this quasi-static and non-quasi-static process, there is a reversible and irreversible. So just if you can go through that one, the reversible process means it is possible to attain the initial states after eliminating the effects introduced to obtain the final state, right? So if at all any friction is there, if you remove that particular friction, the system will come back to the initial state. But in case of irreversible process, it is not possible to attain the initial states after eliminating the effects introduced to obtain the final state. So initial state will always be different in reverse process. So all the quasi-static processes are reversible in nature, whereas in the irreversible process, all the non-quasi-static processes are irreversible in nature. So the process will become reversible by eliminating the causes of irreversibility. So that is the resisted expansion of gases, no intermolecular friction or external friction. So this comes under to the reversible process. Here, what are the causes of irreversibility? So one thing is, if a process is going to become irreversible due to because of these reasons. So one is internal friction between the molecules. Second one is the free expansion of gases or the throttling process, free expansion of gases, throttling process, paddle wheel work, that is the braking action causing the conversion of mechanical work in the form of a heat. So it is not possible to obtain the motion of a wheel by supplying the same amount of heat to the wheel. So this is going to cause the irreversibility. So in a reversible process, the cyclic integral of change in heat transfer with respect to the time, that is the cyclic integral of that is let me write that the cyclic integral. So this is the cyclic integral of dq by t. Cyclic integral of dq by t is equal to 0. So this is the cyclic integral, that is dq by t is equal to 0. In case of a Clausius inequality, dq by t is less than 0 for a cyclic process, or the change in entropy for a reversible process of ds not equal to 0. For a reversible process not equal to 0. So that is the reversible and irreversible process. Sometimes the question is going to appear as differentiate the reversible and irreversible process. So for a reversible process, once again, reminding that here the process is going to be as a continuous line. So 1 to 2. Whereas in case of a irreversible process, it is represented as a dotted line, that is 1 to 2. So it is a dotted line. So this is the irreversible process. This is the irreversible process. Next, a thermodynamic process is going to set reversible. Thermodynamic process is going to reversible if the system passes through a continuous series of equilibrium states. Continuous series of equilibrium states. All the intermediate states must pass through the equilibrium point, equilibrium state. So when it is possible? When there should be no friction. If no friction either in the solid or liquid, then the system comes back to the initial position. Second point, the heat exchange to or from the system. That is, if any, should be only through the infinitely small temperature differences. Next, The process should be the quasi-static one. So it should proceed at an infinitely slowly speed, at an infinitely slow speed. So all the states are in thermodynamic equilibrium in a reversible process. So the process can be run in any direction. So this is nothing but a reversible process. So what are the examples we can consider for this? So in so many competitive examinations, this type of examples they may give. So what kind of a process it is? Is it a reversible or irreversible or isothermal? Something it is going to mention. So for a reversible process, the examples you can consider it as a motion without a friction, restrained and controlled compression expansion process, isothermal and frictionless adiabatic process, elastic stretching of a spring solid, restrained discharge of a battery. See, restrained discharge of a battery. That is very important for competitive exams pointer. Electric circuit with zero resistance. So, electric circuit with a zero resistance. Polarization and magnetization effects and electrolysis. So, these are the examples we can consider to the reversible process. In irreversible process, when we can say that it is a irreversible process. So, if a process is called irreversible, if a process is called irreversible, if the system and all parts of its surroundings cannot be exactly restored to their respective initial states after the process is completed. So, if the system and all the parts of a surroundings cannot come to the initial states once the process is completed, then you can call it as an irreversible process. So this is what, so in an irreversible process, where you need to place that it is in terms of the dotted line. So if it is a throttling process, then you have to mention it as a dotted line. So this is 1 to 2, right? Dotted line. The compression and expansion, the directions which you need to mention. A process is reversible if both the system and surroundings can be returned to the initial states. Process is reversible if both the system and the surroundings can be returned to their initial states. Say, for example, if you take the refrigerator. In a refrigerator, the thermodynamic properties, in a there is a process, the series of processes which are going to take place, and one cycle is going to complete. So all the thermodynamic properties will come back to the initial state in case of a refrigerator, right? Or in case of a thermal power plants. So once the water gets heated, first initially the water at atmospheric temperatures have some properties. Once the cycle is completed, the water properties will come back to that is the steam properties will come back to the initial state condition. So for a irreversible process, that is it is the subject matter of a second law of a thermodynamic process. So the reversible process are considered again in the later section, that is in the second unit. So many problems we need to solve. So the second law can be used to determine whether both the system and the surroundings. The second law of thermodynamics can be used to determine whether both the system and surroundings can be returned to their initial states after the process has occurred. So this is the second law. This can be used to determine whether a process is reversible or irreversible. So only from the second law you can judge or you can justify. So whether that particular process is reversible or irreversible from the second law of a thermodynamics. So if a system undergoes a process, irreversibility may be found. Irreversibility may be found within the system as well as with the surroundings. Although in certain instances, they may be located predominantly in one place or the other. So for many analysis, it is convenient to divide the irreversibilities in two ways. That is, one is the internal irreversibilities, which are those occur within the system, external irreversibilities, which are those that occur within the surroundings, often the immediate surroundings. So internal irreversibilities are there, external irreversibilities are there. So what are the examples are encountered into this irreversible process? So when a heat transfer occurs through a finite temperature difference, so that is it is irreversible. Unrestrained expansion of a gas or liquid to a lower pressure. Spontaneous chemical reaction. Spontaneous mixing of a matter at different compositions or states. Friction, the sliding friction. The sliding friction as well as friction within the flow of the fluids. Electric current flow through the resistance. If it is a zero resistance, it is a reversible process. So electric current flow through a resistance, that it is the irreversible process. Magnetization and or polarization with hysteresis, inelastic deformation. So these are the examples you can consider over here. So in case of irreversible process, there are two processes which comes under to the irreversible side. So that is, one is the free expansion of a gases against the vacuum. So one is the free expansion of a gases, that is the one process. Second one is the throttling process. So the second one is the throttling process. Right? So these are the irreversible process. So this particular diagram and sketch, which is already discussed in case of quasi-static and non-quasi-static process. So I think you have got the idea what is meant by quasi-static process. A process which occurs in an infinitely slowly, and all the intermediate state points are in thermodynamic equilibrium. If this condition is satisfied, then we can call it as a quasi-static process, right? So the reversible, you can also call it as a reversible process. So the constant pressure process, constant volume process, isothermal process, polytropic process, adiabatic process. So these processes we may consider it as a reversible process, right? Next, after that, we need to consider the homogeneous system, and in the first class we have also um, given a small glimpse onto the homogeneous and heterogeneous system, right? So homogeneous system means nothing but it is a quantity of a matter throughout in chemical composition and physical structure. Quantity of a matter which is homogeneous throughout in chemical composition and physical structure is called a phase. So every substance can exist in one of the three phases, that is a solid, liquid or gas. But if a system consisting of a single phase is called a homogeneous system, while a system consisting of more than one phase is called a heterogeneous system. So the examples for the homogeneous system where you can consider it as a ice, water, dry, dry saturated steam, mixture of ammonia in water, mixture of air and water vapor, water plus nitric acid. So these are the examples comes under to the homogeneous system. The examples comes under to the homogeneous system. That means more than the one phase. So mixture of ice and water, mixture of non-miscible liquids, that is water plus mercury, water plus gasoline, wet steam, that is vapors in contact with liquid being evaporated. So these are the examples you can consider under to the heterogeneous system. So in the fourth unit, there is a pure substance topic is there. So that is it is related to the properties of a steam. So what is meant by a pure substance? That also we should have to learn. So matter can exist in three phases, namely you can call it as a solid, liquid or gaseous phase. But a phase is defined as a homogeneous part of a system surrounded or separated by a boundary surfaces having the same intensive properties. You can call it as a phase. So phase is defined as a homogeneous part of a system separated by a boundary surface having the same intensive properties. So a pure substance is treated as invariable chemical composition in all its phases. Examples you may consider as an example, mixture of ammonia gas and ammonia liquid, it is a pure substance. Next, mixture of that is steam and water, it is also the pure substance. Air, though air is consisting of nitrogen and oxygen, if it is if the air gets heated or if the air gets cooled, right? So air gets heated or air gets cooled, invariable chemical composition is there. So that's why we have to treat the air is also a pure substance. But if you carry the air or if you are trying to liquefy the air, the proportions of nitrogen and oxygen are going to vary. The chemical composition is also going to vary. So in that instances, air cannot be considered as a pure substance, right? So if the air undergoes the liquefaction, in that case, air cannot be treated as a pure substance. When in the normal sense, the air is considered as a pure substance. So this is all about for today's class.